Hello. In this video, I'm going to go over our final example problem of analyzing stress at a point and stress transformations. So, in example 4, you can see I have a different problem set up than the other examples. And this one is set up with two parts. You can see here we have original plane stress element with axes P and Q, and 28 degrees down from the P axis, we have an N and T system. And it is the N and T system that we have values for normal stress. So in the two parts of this problem, in part A, we have to calculate the stress on plane AA, and in part B, we have to calculate the stresses in the PQ system. So in part B, that's really kind of a working backwards problem where you can see you have the original stress and there's a stress transformation going on here, and we have the values for that, and we have to basically transform back to P and Q. Part A is you can pretty much treat like N and T is its own plane stress system, and you're doing a stress transformation from that to find the stress on AA. So the way we're solving AA is we're first setting x1 and y1 to be collinear with N and T respectively, and then you can see we're rotating x1 45 degrees to be in line with this AA plane. So that would make a theta of N to x1 45 degrees, and y1 is perpendicular to AA. Remember, there always has to be a counterclockwise 90-degree angle from x1 to y1. So we can plug in all this information. Sigma n would be -20, sigma t would be -3. The shear stress is 0, 45 degree. We're plugging into our stress transformation equations, and we find sigma x1 to be -11.5, sigma y1 -11.5, and then a shear stress of 8.5 ksi. And you can see I've already added the two normal stress sets together, and they both come out to the same value. When solving this with MechMat, here let's pull up our stress transformation. So our values are -20, -3, and 0. You can see in the element it doesn't show any shear stress because we put in 0. Okay, and we are just transforming at 45 degrees, so we can just put that straight in. And here are our values: -11.5, -11.5, and 8.5. So that's really it for part A, and we can move on to part B. So as I said before, N and T are a transformation from P and Q, but in this part we're basically working backwards. We're taking N and T and transforming up to P and Q. So you can see it's already written on the figure originally. Our angle theta from N to P is 28 degrees. So we can set x1 to be collinear with P and y1 collinear to Q. At this point, there is nothing really more to do but plug this into our stress transformation equations. All the values are the same. The only thing that we're changing is our theta, which is no longer 45 degrees, it's 28 degrees. And when you plug that in, you find that sigma x1 is -16.25 ksi, which is sigma p. Sigma y1 is -6.75 ksi, which is sigma q, and the shear stress is 7.05 KSI. Now, we already had our information here for the stress transformation of part A. The only thing we're changing is our degrees, or theta, which is 28 now. Hit change, and we have these same exact values pop up instantly. So that's all there really is to it. It's just kind of the ideas of how you can place our x1 and y1 axes, and at least for part A, you can treat n and t as its own plane stress and transform from there to get AA. And then for part B, again, you're transforming from n and t just back to align with P and Q, the original set.